Hello and welcome to today's webinar. The webinar today is jointly presented by HydroComp and FRIENDSHIP Systems, and we want to talk about how the software tools NavCad and CAESES can be combined for the design and optimization of ship hulls. My name is Matthias Brenner, and I will guide you through this webinar on the side of FRIENDSHIP Systems, and I'm joined today by Don McPherson, who will take care of HydroComp's side. Hello, Don. Good morning for you, I guess.
Yes, indeed. Good morning. Very pleased to be with you here today, Mattia, and let me extend my personal welcome to all of the participants.
Thank you. So a few introductory words about ourselves. Don is the CTO at HydroComp, where he is responsible for the development of the software and the technical services that HydroComp has to offer. And he co-founded HydroComp in 1984, so quite a while ago, and he has a background in naval architecture. Myself, I'm responsible for sales in Europe and the Americas at FRIENDSHIP Systems. I've been with the company for about 10 years, so a bit less than Don at HydroComp. And many of these years I spent working in the pre-sales and engineering team before I transitioned to sales. And my technical background is in naval architecture as well. So let's see what we have on the agenda today. First of all, I will give a few words of introduction about FRIENDSHIP Systems, the company, what we do, and specifically about our software CAESES. And then Don will tell us the same about HydroComp and NavCad. And for the rest of the webinar, we would like to look at a specific application example. And we will start by presenting the case that we're looking at. And then we will talk about the geometry model that we set up for geometry variation. Then the calculation setup in NavCad and the optimization setup with the two softwares combined. And finally, we'll tell or discuss a little bit the optimization results that we obtained for this case study before we wrap up everything. If time allows, at the end, we will have a Q&A session. And in that regard, there is also an announcement to make. You can see in your interface, in your GoToWebinar interface, that you can type in questions. So whenever you have some question that comes up during our presentation, then please enter it there, and we will try to pick out some questions at the end in the Q&A. And if we don't answer your question, then we will follow up after the webinar. So feel free to take that opportunity. So as I mentioned, let me get started with my side about the company FRIENDSHIP Systems. We have been working for about 15 years, specifically in the fields of geometry parametrization and optimization. And we basically partner up with our customers to solve any kind of problems that they encounter in a so-called simulation-driven design process or performance-driven design process. And we started working in the maritime industry, and for the majority of the life of the company, we were focused solely on the maritime industry. And only in the last maybe 5 years, we started expanding also into other industries that are also dealing with, let's say, flow optimization, geometry optimization problems, such as turbomachinery, powertrain applications, and so on. The company is located in Potsdam in Germany. And what you see here on the side is unfortunately not our office building, but one of the beautiful palaces that you can see in Potsdam. So it's certainly worthwhile to come to Potsdam, not only to visit us, but also to do some sightseeing. Our main business is a software product, which is a CAE platform called CAESES. And I want to tell you a little bit more about that. So what is it that we do with this software? CAESES is mainly composed of two components. The first one is everything that has to do with the optimization process. So to run an optimization, you need algorithms to drive the process. A lot of data is generated, geometry data, calculation results, and so on. So that needs to be managed. And all that data is also needed to make design decisions. So we need some assessment tools so that we can sort through that data and draw the right conclusions. The second component of our system is everything that has to do with the CAD modeling and CAD description of a geometry. And here we have a very specialized CAD tool in our software that has a focus on providing simulation-ready geometry that can be used directly to run any kind of computations with it. And most importantly, we have a focus on geometry variation. So you have a geometry that you want to change in an automated process, and that should be easy and robust, as well as described in an efficient way. And to complete the process, we provide the generic interface that can be used to couple any type of external tool that will provide some kind of performance feedback about our geometry during the optimization. In this case, it will be NavCad, and Don will say a little bit more about that after my introduction. So just some questions to get started. Why should I automate my design process? Maybe it's more or less clear, but the situation nowadays in terms of laws, regulations, but also the competition on the market demand that the designs that are generated in ship design have to have a very high level of performance. And let's say an old iterative manual process is not necessarily suited to achieve these high levels of performance. So in this manual process, we would maybe create a CAD geometry, then run some kind of performance prediction calculation, CFD, or some other type of calculations, do post-processing, based on the results, decide to make some changes, and go back to the geometry, make the necessary modifications. And that, of course, is time-consuming, which leads to higher development costs. And it can lead to certainly an improved design, but not necessarily an optimized one. So that in the end, maybe it's not possible to reach the performance target that has been set for that design. The automation, of course, I think that's pretty clear now, can shorten these development times, reduce design cycles, reduce the amount of experiments maybe also, and lead to better and optimized designs. I think that's, so to say, the opposite of what we heard before. But also an important point, I think, is that it can increase very quickly the knowledge about the product's behavior in the early design phases, so that you can understand very quickly what kind of impact your geometry parameters have on certain performance characteristics. And one of the goals of CAESES is to give you a control over this complete process, over this automated process from one integrated user interface. Another point is, I mentioned, an important component of CAESES is the CAD modeling part. So the question might be, why do I need another CAD system? Maybe you already have some CAD system for line design and so on. And actually, from our experience, we can say that most of the bottlenecks that we encounter when people are trying to run a design exploration or optimization process are related to the handling of the geometry. So this could be the geometry variation is tedious, so it's very time-consuming, difficult to make specific changes to the geometry, or it's prone to failure, that when you try to change something automatically, the geometry breaks down. Also, complex geometries might have way too many parameters to be involved in an optimization process in an efficient way. Constraints are an important point. It might be difficult to consider or fulfill specific constraints that we have on our design during the optimization. And finally, if you're coupling to a simulation or calculation tool, the quality or the way that the geometry is available is not necessarily suited for that tool to be used right away. So if you want to run a CFD computation, you need to generate a mesh, and the geometry that you provide to the mesh generator might not be watertight. There might be things to clean up, and that, of course, is not suited for automation. So these are the things that we're trying to address with our specialized system in CAD system in CAESES. Finally, how can I make use of CAESES in the context of marine applications? You can see here a couple of examples from going from ship or boat hulls to energy-saving devices, propellers, but also offshore structure, renewable energy systems that are located in the marine environment, things like that. And you also see a geometry variation on the side. So I think, or I hope, this will give you an idea of what we do here at Friendship Systems and what our tool is supposed to do. And now I would like to switch over to Don, who will tell us a bit more about HydroComp and their system NavCad.
Thank you, Mattia. Advance, please.
Yes.
HydroComp is a small research consultancy with a specialization, as I write down here, in operational hydrodynamic and propulsion system simulation. Well, that's a big phrase, but it faithfully encompasses what we do. A couple of the important brand characteristics of HydroComp is that we focus on applied engineering as opposed to theoretical engineering. We take the work that is done in academic institutions and research studies, and we apply them and make them available for naval architects to use during their normal course of business. Now, of course, we have our own in-house R&D program that is very active, but that tends to focus on the application of technology as opposed to the novel creation of technology. Although in the case of propulsor design, we have a very active novel R&D program in-house as well. We're located in Durham, New Hampshire. That's a short distance north of Boston. And as Mattia indicated, we were founded in 1984. I was one of the founding partners. So we've been at this game for a long time and still continue to enjoy every day that we do in this work and in this domain. Our activities at HydroComp are both in software and technical services. The performance simulation, the prediction of resistance and propulsion and speed and power is our principal work, but we are actively involved in what we would term forensic analysis, trying to identify why ships and marine vehicles behave the way they do. Sometimes they're not performing up to expectations. Others, it's just a matter of trying to document some of the underpinnings and details of performance. And as mentioned, we're also very active in propulsor design. The little illustration that we have in the lower right hand is just an example of some of the work we do on small thrusters, for example. We're quite well known as a designer of thrusters under 1 meter for ROV, AUV applications, for example. The software, the software products that we're most well known for, of course, is NavCad, and we have two editions of that, the standard and the premium, and it's the premium edition that we will highlight here because of the interactivity that's necessary to connect with CAESES. We also have a blade element design code for propellers called prop elements, and we serve a large segment of the international propeller manufacturing community with our geometric modeler called PropCAD. What we do in the context of this discussion is to provide that simulation solver that was very ably described by Mattia in the CAESES setting. The software connection that we will describe here is a NavCad specific connection for the simulation of not only component pieces, but really more broadly, the propulsion system simulation. So let's proceed to the next slide, and we'll get into some of the details of what that particularly means. I would like to propose the idea here today that NavCad Premium is a critical simulation solver for marine design with CAESES, and there are 3 points that I would like to make in support of that. One is that NavCad provides for simulation of the hull, propulsor, driveline, engine system. And I want to distinguish between that system and the components of the system. Because at the end, what we're really looking for are system-based outcomes, whether that be fuel consumption or CO2 production or minimum energy. The objective functions that we will talk about sometimes are component-based, hull and propulsor, but most often they are system-based. And NavCad gives you that framework for the hull, propulsor, driveline, engine system to be able to observe and evaluate whole ship system across a mission-based duty profile, for example. Now, within NavCad, in support of that system, we have a variety of fast and efficient, what we term 1D and 2D component performance models. And by component, I mean hull prediction models for resistance or hull propulsor interaction, for appendages, for added resistance in seas. On the propulsor side, we have propellers, water jets, different kinds of propulsors, and then the components for the driveline, the shafting and transmission, and the engine or motor or prime mover that actually provides the energy to the system. So you can build up the system with NavCad's 1D and 2D component performance models. And we'll see how that reflects different order models here in just a moment. And within the design spiral, which is the classical illustration I've put on the right-hand side, NavCad, with its data exchange with CAESES, for example, allows you to view early stage design studies very thoroughly and then still maintain that system throughout the different levels of the design spiral as your program matures. Now, I want to take a moment here to talk about how NavCad complements the CFD solvers that you might be using or might propose for use with CAESES. There's a few things that NavCad can do in the context of CFD use with CAESES to actually improve the effectiveness and efficiency of your entire workflow. One is the ability to use existing or reduced sets of CFD calculations. NavCad has the ability to conduct what's called an aligned prediction. Most frequently, this is with model test data. But what you can do is you can use sparse calculations of CFD, apply that with NavCad, one of its 1D and 2D prediction methods for bare hull resistance, for example, and use a reduced number of CFD calculations to bring back into the NavCad setting to align the reduced order calculations, the component performance models in NavCad to really improve the total efficiency and reduce the time to results. A very, very important part of any kind of a design spiral or evolving or maturing design is the ability to use reduced order methods as benchmarks for the higher order calculations. We need to have an idea before we flip the switch on CFD what the answers are going to be, so that we can ensure through benchmarking that our gridding is correct, our CFD settings for the analysis make sense. And NavCad can provide those benchmarks for you to establish confidence in the CFD predictions. Of course, in conjunction with CAESES, you can do design space optimization prior to employing CFD assets at all as a solver for CAESES. And I would offer that as an extremely valuable process to introduce into your workflow, where if you can get to a narrower design space with the faster simulation that's available with NavCad, you can reduce the amount of time that you have to spend with higher order solvers. You can focus the higher order solvers on the very valuable design space that you want to optimize. And then we can establish starting conditions for CFD convergence. Planing hulls are a great example of this. With NavCad, you can come to the table with a sinkage and trim value. This is true for non-planing vessels as well. So that can provide starting conditions for your CFD convergence. So everything about the complementary nature of NavCad with CFD improves your CFD outcomes. And this last point here is NavCad Premium is the one tool that hits that what I term sweet spot between facility and precision, how effectiveness or capable something is, and the necessary precision for the design stage that you are considering. This makes it especially valuable for early stage design. So here's some thoughts that I would like to share for those of you actually beginning to use NavCad with CAESES about how can you best use it. Well, one thing is NavCad can predict a variety of performance metrics as part of the whole ship system. So I was talking a moment ago about how total mission fuel consumption might be one of the objective functions that you would use. So the CAESES optimizing objective functions should be based on one of the NavCad metrics, such as minimizing bare hull resistance for a component analysis, which is what we will see here in the case study, or perhaps a full voyage fuel consumption, where you can create a whole operating mode's mission duty profile and then get an energy metric and minimize that as the objective function itself. So the choice of the performance measure that you use really should reflect the maturity of the design and the system characteristics. In this particular case, we're using a vessel with a water jet as a propulsor. Well, water jets, like main engines, are a component. We don't design individual impellers or nozzles or inlets. So we have to take the characteristics of the water jet as a whole. So in this particular case, it makes sense for the objective function scope to be based on a component, because we're then going to plug in a water jet as a propulsor later on. Now, if we were doing propellers, for example, controllable pitch propellers, fixed pitch propellers, we might include optimization within NavCad of the propeller itself. So now we have kind of nested optimizations that can lead to, truly optimized systems with CAESES for mission critical outcomes. So with the objective function scope, we talk about components leading through to system. Component optimization metrics might be hull resistance or its equivalent effective power. And we'll want to keep that in mind. Telfer coefficient is one that we use frequently because it normalizes resistance for displacement. It's the equivalent of a resistance weight ratio, except that it's truly a non-dimensional coefficient, so it's unit in-specific. System objective functions would be engine power, fuel consumption, or even emissions, which is something that we are getting into. Just as a quick sidebar, we also are seeing design drivers that are not related to the traditional thoughts of efficiency, and we're beginning to use objective functions for things like hydroacoustics and underwater radiated noise. Now, the operational scope that you might want to consider when setting up your session between NavCad and CAESES is, do I want to look at a single design point, which is the example here, a simple weighted function, or perhaps a full operating modes analysis like I described earlier? Now, a single design point just is one speed. Now, we have a vehicle that has a principal speed as its mission. So a single design point is sufficient at that point. Now, we can use for a component-based outcome a simple weighted function where we only have a single mode, a transit mode where we're just moving from point A to point B, or perhaps a towing mode where we want to look at multiple speeds and a weighted time. It's critical that you remember not to use resistance for this, that you use effective power. Power is a better way to communicate energy. Resistance is speed specific, so you want to actually look at what the power or equivalent energy demand is, and that's captured through the use of effective power as opposed to resistance. In the case of a single design point, it doesn't make any difference, but if you're using multiple speeds with perhaps a simple weighted design point, that you want to remember to use effective power. And then a full operating modes scope, multiple modes of varying transits, towing, idle. A vessel with a search and rescue mission is a great example of this. That wants to be time weighted, and you can then look at total energy key performance indicators, even something like CO2 production, as a scope for an operational scope for your objective function. Now, one way of improving the CAESES-NavCad effectiveness is to do some preliminary optimization within NavCad before you begin your more broad optimization within CAESES. And I would just like to introduce you to NavCad's drag reduction utility. This is not an optimization utility. What it is it takes the parameters of the prediction method chosen, and it does a simple two-speed weighting. And for your total energy or your weighted effective power, it will look at the primary speed, the secondary speed, and give you an indicator as to how your parameter has to change. We want to increase length to reduce drag. We want to decrease wetted surface. That becomes obvious. Decrease displacement. That's also obvious. But we can begin to see other design items, half angle of entrance, draft, immersed transom area that we'll see is important in this particular case, longitudinal center of buoyancy. These are things that we can then begin to use and as an initial guidance for how we want to set up our optimization in CAESES to say, NavCad suggests we might look here. And so let CAESES begin to look in that domain, in those regimes first.
Okay, thank you, Don, for this thorough introduction. So let's start looking at a practical use case of this coupled system. So the example case that we picked out for this is a as was mentioned already, water jet driven boat, a patrol boat, which has a round bilge hull shape with an immersed transom stern. The length of the vessel overall is 29 meters and the beam is 6.8 meters. And some preliminary analysis that was done on the hull form indicated in terms of speed prediction that 23 knots could be reached as a top speed rather than the 26 knots that were promised in the tender of the vessel. So obviously you can see there is a lack of speed that the vessel can reach, and one option was that for the builder of the vessel to introduce a larger engine, but of course that brings a lot of negative points, and so it was the focus was put, let's say, first of all on the hull form to see how much can we gain in terms of the hull form without having to increase the engine, and also in a further step to select the most suited water jet in combination with the hull that we have and the engine. So to narrow it down again, the target was to reach the 26 knots and find the best hull form with regard to the resistance, and then afterwards find the water jet suited for that. So the first step that we have to do for this optimization task is to get the possibility of changing the geometry of our hull form, and this can be done basically with two different approaches in CAESES. The first one is we set up a parametric model of the hull form. So basically we generate the hull lines, a model of the hull geometry from scratch, and define parameters that control this geometry. And the second option are morphing or deformation techniques, where you import an existing hull form and apply some kind of changes to the geometry. So for the first approach, the advanced parametric surface modeling that we offer in CAESES works in such a way that we create, first of all, a curved template. So this is a cross-section through our surface. You can see it indicated on the hull form on the right. And in the bottom, you see a picture of that cross-section. So this is a frame of our hull that is controlled by some parameters. I put in here a couple of parameters, might not be all of them, but to give you an idea that we can control the frame shape with parameters. Things like the height, the beam, and so on, but also angles like the dead rise angles, or integral values like the submerged area, cross-sectional area, things like that. And if we move our cross-section or frame, in this case, along the surface of our geometry, the values of the parameters of this template will change, and that can be described through parameter distribution functions. So you see in the bottom in the picture some of these functions for the hull. So we have some, let's say, physical curves like the deck contour and the center plane curve, but also some other curves that indicate how the dead rise changes along the hull and things like that. And if we combine these two things, our cross-section template and the parameter distributions in the sweep direction of the surface, we can generate our surface. And by controlling these parameter distribution functions, we can control the shape of our surfaces. And this is a very, let's say, efficient way of describing a quite complex freeform geometry in a flexible way, but with a low number of parameters. So this is something about the fully parametric modeling of a geometry. And in this case, actually, we use the second approach that I introduced, which is the morphing. So we have an existing geometry, a baseline geometry for this hull, and we would like to apply some changes to this imported geometry. And here I have some animations that show the parameters that we were able to change. The first is length. So this is basically a simple scaling of the geometry in longitudinal direction. Then we have the ability to change the beam of the vessel. So also sort of scaling in transverse direction. Then the third parameter is the draft of the transom. So we can control the immersion of the transom, sorry. As you can see in the animation here. Then the dead rise at the transom can be changed. The shape of the deck and the design waterline. So basically, I hope you can see it well enough in these animations. It's basically also similar to a scaling, but it's more localized, so that basically we increase the beam at the maximum beam position of the deck, and that also has an impact on the design waterline shape, so they're, let's say, changed together. And finally, we have the volume distribution. So here we redistribute volume of the hull in longitudinal direction. So basically, this has an effect on the center of buoyancy also. Well, once we have our variable geometry model that can be controlled by parameters, so when we change the parameters, we can obtain different variants of our hull form. Once we have that, we need to export the geometry to our downstream tools that make the performance assessment, and the geometry can be exported in, let's say, different types of generic formats like IGES, STEP, STL, and so on. So all, let's say, surface-based formats, or in this case, we transfer the geometry to NavCad using a specialized input script that contains all the necessary information about the geometry. And that, in CAESES, is automatically filled with new data for each hull variant during the optimization process. So what you can see here on the right is the user interface of this customized export that we have written. And here you can fill in a couple of data that is necessary. You can provide the hull form geometry, specify the hull type, the prediction method that you want to run, and then this export function will generate a script that looks similar to what you can see here in the picture, that contains all the information for NavCad and also controls the NavCad process. And just to highlight here specifically, what is also transferred here is the shape of the hull in terms of data at specific longitudinal positions. So we have, first of all, a list of longitudinal positions, and then we provide the beam, the waterline beam at that position, the cross-sectional area, and also the centroid position of that cross-sectional area below the waterline. And this is basically what you see here in the plots at the bottom. And this gives NavCad all the information it needs about the shape of the hull. So this is how we transfer the geometry, and to connect the two tools, we use our so-called software connector, which is the generic interface I mentioned at the beginning to connect CAESES to external tools. And this is a, let's say, generic view here that shows the 4 quadrants that we have in the software connector. In the top two one, we have all the input that is supplied to the external tool, the geometry on the one side, and also all the additional input files that we need on the other side. And in the bottom, we can specify all the result files that we want to load into CAESES after the calculation has been finished to evaluate certain values for our optimization process. So on the one side, we can provide files that are read in as whole. So you can create screenshots, you can import flow fields from your CFD solver to do post-processing in CAESES, things like that. And on the other side, we can specify specific values that we want to read from a file to be used for, as an example, as an objective function. This is how the software connector looks like for the NavCad case. So in our input file quadrant, we have the script file that is generated by this automated tool I showed you before. Here in the middle, we have the link to the executable, which is a special executable that runs NavCad with the script. And then we have some screenshots that we're loading as a result file, as well as a text file that contains output values that we read into CAESES to use as an objective for the optimization. Okay, and now I would like to give back to Don, who will tell us a little bit about the computations that we're doing within NavCad in this case, and then we continue with the optimization.
Sure, thanks, Mattia. Just a couple slides here to describe the methodology and the application of the methods that will be used inside of NavCad for this. Mattia mentioned how they are capturing distributed volume data and other parametric data of the hull form and passing that into NavCad. Well, the kind of data that is used, I wanted to describe the two component prediction options for bare hole resistance here as a way to introduce you to the idea of 1D parameter-based predictions and 2D volume-based predictions. A parameter-based is one that most people will be very familiar with, very popular methods that might be based on systematic series or random data methods, where the data is in a one-dimensional parametric form: a length, a beam, a draft, displacement, max section area, longitudinal center buoyancy, for example. The prediction are empirical. That they use statistical methods of systematic series or a variety of different hull forms in order to take these parameters, typically create polynomial functions or other kind of statistical based functions to create a prediction. Now that has a scope, and in the case of NavCad, we have some 40 different parametric 1D based prediction methods for hull form that will support, small go fast planing hulls all the way through to the largest tankers and bulkers. A volume based prediction is what we're calling a 2D method. Really, we're looking at the hole in the water, the immersed volume. And because in CAESES we have the ability to refine geometry with longitudinal distributions, unlike higher order solvers where they're looking at the surface envelope, what we're doing is we're looking at the longitudinal distribution of the immersed volume. And inside of NavCad, we call that our analytical distributed volume method, which is a novel linear wave making code that has appropriate corrections for a variety of viscous drag contributions of form, boundary layer thickness, etc. But also it has predictions for sinkage and trim corrections, so that throughout the speed range and throughout the vessel types, you can use the analytical distributed volume method to look at refinements in hull forms and outcomes in a much more detailed way, yet still to be extremely fast and time efficient. Another advantage of this kind of a 2D method is that it's very well behaved. And in the graphic on the lower right there, what I have done is shown a stern with a propeller pocket, very popular for motor yachts and patrol craft, for example, with a conventional shaft-driven propellers. Well, if the waterplane or a waterline slice were to happen to go through that, you can see that there is shape discontinuity in that slice that does not allow a lot of other comparable linear codes to function properly. By looking only at sectional area, waterplane distribution, and the vertical immersion of the sectional areas, we eliminate those problems. And so this method is extremely well behaved and provides no disruption in an optimizing session where you're going to be looking at many, many different variants. The application that we would propose and used here in this particular example is to employ the hull variation changes that you get with CAESES by pre-establishing the project settings using the NavCad interface, an example of which is shown here. So we would propose to set up an initial project file template that you would begin with, and then allow the hull form to change iteratively for each variant session from NavCad inside of CAESES, and let CAESES indicate, here's the new hull, here's an opportunity to recalculate that. Let me capture the results for this modified hull. So units, vessel speeds, water properties would all be common. We would propose to define any environmental drags that you want to consider if you're looking at a system-based prediction, added resistances in wind, seas, shallow water, for example, any appendages that you might have. In this particular case, where we're looking at a single duty point, a single design point, and water jet driven, we don't have to worry about those kinds of added resistances. We're going to use the ADVM method as described for resistance and set up our preferences for the kind of viscous expansion that we want to use for presentation of the results. What prediction of form factor will we use, a correlation allowance, friction line, all of those changes the way the results are presented. And then we can save this NavCad project file as the calculation template for the analysis of all the variants that we will get through our CAESES session.
Exactly, and that brings me to the next step, the generation of all the variants and the optimization process. So in terms of the optimization setup, we saw before when I introduced the geometry variation that we have six free variables for our hull form, and we have some constraints on displacement and center of buoyancy, so we are only allowing small changes in these values. And our objectives specifically are the resistance at 22 and 30 knots. So we're evaluating the resistance of the vessel at these two speeds and trying to minimize it. And in terms of the process, we ran a DOE, or we started the process with the DOE of 500 designs, which is very quickly, of course, because the calculations here are done very, very rapidly. And we follow up this DOE with a local optimization. So when we have identified some good areas in our design space through the DOE, we can run local optimization within these areas. In the table here at the right, you can see the design space, so the lower and upper bounds of the different values. Some of them are the, let's say, the input variables that we're using. Some are outputs of the system. But this is, so to say, the design space that we're covering with our DOE DOE setup. So once we ran the process, we can, of course, get specific results. So we would be able to get an optimized design as a result, but also an interesting point that we already get in the meantime, also as a result of our preliminary DOE, is that we can identify very well the influence of the different free variables on our resistance objective. So as you can see here in the picture on the right, we have some correlation plots that show the correlation between the design variables that are shown in the column headers and our objective functions that are in the row headers here. And here we can see, I mean, these are not all the free variables, but a few of them. And we can see that we have a strong influence of the transom draft or the immersion of the transom, as you can see from these diagrams. So that has a strong linear correlation to the Telfer coefficient at 22 and 30 knots. We have a, let's say, medium influence of the transom dead rise angle. So there is certainly an influence, but it's less pronounced as the transom draft. And other things like the deck and design waterline shape that are controlled by one variable, this is the shift deck here, have a negligible influence on these results. So this is the kind of knowledge that you can gain by looking at the results and understanding how your system reacts to certain changes. Finally, of course, as I mentioned, we also obtained a specific optimized design, which we can see here in comparison to the parent or baseline design. So in the first column here with values, we have the particulars of our parent design, and then in the last column we have the values for our proposed optimized design. And if we look at the results here in the geometric comparison, what we just saw in the figures, the changes that were introduced is we have a slightly more slender hull with a narrower entrance. The transom area is, the immersed transom area is bigger. We saw that the transom draft had a significant influence, and our longitudinal center of buoyancy is shifted slightly aft, and we have a little bit more displacement overall for the vessel. So in terms of the results, you can see here the resistance plots over a range of speed for the parent hull in red and the optimized hull in green. So here we see nicely that over the whole speed range, the resistance was reduced. And if we have a certain, let's say, resistance budget that we can overcome with our propulsion power, then we are able to increase the speed significantly above or beyond the 26 knots that was required for the vessel. And also, if we look at the Telfer coefficient, we can see that the optimized hull was improved over the whole fruit number range. And again, we are able to achieve a higher fruit number. And specifically, if we look at the improvement at 30 knots, which was one of the target speeds for which we optimized. If you remember, we had resistance at 22 and 30 knots as the objectives for the optimization. Here we can see that the Telfer coefficient was reduced by 8.2%. There is also the explanation of Telfer coefficient if you're not familiar with it. So this was the resistance optimization that we performed on the vessel, and now the last step was to select a more suitable water jet for this optimized hull, and that Don will tell us something about that.
Certainly, just a brief comment on how water jets are dealt with, and in the context of this particular case study example. Can you advance the slide, please?
Yes.
As mentioned earlier, water jet performance is not conducted in a first principles way like we might do for propeller design, but it is a component that we have to select, unique individual product models from manufacturers, and they produce data for that purpose, speed, thrust, power, RPM against different impeller types. And so even so, we can use different water jets singularly as part of the optimization, because we can then compare, once we have improvements in the hull form, we can then look at that improved hull against our collection of different available water jets, find the water jet that achieves the highest efficiency at that speed, which is one characteristic of analysis with water jets that's often missing, is that the speed, thrust, power, RPM data that is given, you need to evaluate that in a different form in order to extract efficiency, propulsor efficiency from that. So you may be, as was the case with the initial client of this case study, they were using a water jet that was optimized for 35, 40 knots. It was very, very poor in its efficiency in the 25 to 30 knot range. And so by applying a different water jet and NavCad being able to extract what the propulsor efficiency actually is at that point, the user can then go and select a water jet model to combine with this optimized hull form. And not only that, you can put that in the context of the entire hull, propulsor, driveline, engine system. With the central graphic there, what you can see is that the derivative and final engine power and RPM versus speed can be laid over the engine's power curve, the delivered power curve, to ensure that you have the right impeller, to ensure that you're able to meet speed. And this is showing that the combination of the optimized hull, the newly selected water jet, and the engine that was defined will be able to meet slightly in excess of 26 knots, which was the design objective.
Okay. So let's come to the final results. First of all, let's say by doing all these different steps in the process, in the end, the result is some significant cost savings in different fields. So first of all, in terms of capital expenses when building the vessel, the vessel is supposed to be equipped with 2 engines that are, let's say, in a range of $100,000 each. And the original expectation of the client, when it was noticed that the vessel fell short, was going to fall short of the speed target, the original expectation was to install an engine that was about 20% larger, which, if we scale linearly, is about $20,000 increase in price per engine. So by not having to install a larger engine, the saving is about $40,000 for the engines only. And another factor is the cost savings in operational expenses. So the prediction for the fuel consumption that NavCad gives us at 20 knots, which is the mean cruising speed of the vessel, is about 252 liters per hour for the parent design and 185 liters per hour for the proposed design, per engine, that is. And if we estimate 500 hours per year of operating demand of the vessel and an average cost of marine diesel fuel of $1.05 per liter, that's let's say worldwide average figure, then we reach savings in operational expenses of $72,000 for the fuel. And we can possibly expect some further benefit from the lighter design because we have smaller engines and slightly higher payload possibly of the vessel, but that's not part of the calculation here. So to summarize the conclusions, NavCad and CAESES have been successfully utilized in a coupled solution for the optimization of the ship hull. The data exchange, that's an important factor between the two programs, was automated, so that it's very easy in the automated process to transfer geometry data and result data back and forth between the two programs. And finally, the design challenge of a patrol boat that was falling short of the promised maximum speed could be solved in a two-step process by optimizing the hull for lower resistance and employing more suitable water jet selected by NavCad. And the target speed could be reached, even exceeded a little bit, and substantial cost savings for operational costs and capital expenses were achieved. So this is the conclusion of the webinar, of the content of the webinar. If you liked what you saw today and you think it's interesting, either the combination of the two tools or the two individual tools, then if you would like to get to know these tools more and also find out about the licensing options that we can give you for these tools, feel free to contact us at Friendship Systems through sales@friendshipsystems.com or HydroComp through sales@hydrocompinc.com, and then we will be happy to help you with that. Of course, if you're not familiar with either one of these systems, an option to get started is to run a project together where you can find out on your specific example how these tools work and if they work well for you. And if you're interested in getting one of these tools, then you can use the promotion code SPRING18 until the end of April to get a 50% reduction in price on an annual lease license of CAESES or of the premium version of NavCad. So we are already slightly beyond our finish time. I think we don't have so many questions, but I want to try to address some of these. We have one question from Chris, which is, can CFD and NavCad be combined in one CAESES setup? So the answer is yes. I mean, the advantages of this combination have been mentioned by Don before, and in terms of technical, how things work technically, then of course it's possible in one CAESES project to set up multiple software connectors in a similar way as I showed here on the example of NavCad, so that you can couple CAESES to multiple tools within one optimization setup, and you can also prescribe a certain sequence of execution of the different tools for each variant. Then we have another question from Alvaro, which are the surfaces generated as NURBS surfaces in CAESES? So the answer is yes. The modeling kernel, CAD kernel that we have at the basis of CAESES is a NURBS kernel. So everything that is generated is NURBS geometry and will be exported into a IGES or STEP format and so on as a NURBS surface. So I have a question from Saba about the correlation matrix that I showed on page 33 of the presentation. Let me go back here. This is the correlation matrix. Why the correlation values are not displayed here. We see the graphs, the regression plots, the blue and linear regression, red is the quadratic regression, and actually the background color of these graphs, the orange, green, yellow color, that shows the correlation coefficient. So it's shown in the picture, but maybe it's not quite clear if you don't know it. If we have a reddish hue in the background, that's a big positive correlation. A blue color is a negative correlation, and yellow, greenish colors are in between. We have some questions here. Let me see. I think what is the Telfer coefficient? That was answered. Why weren't the midship parameters not included in the variables? A question from Igor. This is simply based on the choice that was made here. Of course, you can set up a variable for the midship coefficient, either by defining some deformations that are applied to the midship area, as we did here in this case, or if you have a parametric model of the vessel, then one of the parameters that define the geometry can be the midship parameters values. So I think that's simply the choice that was made here. And maybe one question to you, Don, or did you want to comment on this?
Yes, I did.
Okay.
In fact. It's a great question. Midship coefficient, in particular, is one of those things that can be somewhat deceptive in evaluating hull forms. If you might slide back a couple slides here to the prediction methodology page, just because we have a graphic there. Right. What we're really interested, again, is the hole in the water. And for hulls that are like the one that we were using in the case study, a round bilge transom stern, traditionally falling in that semi-displacement regime, the midship position becomes largely irrelevant hydrodynamically. So the alternative to that is to use maximum section area, which in the case of the blue line here, the sectional area curve, we can see and identify what the maximum section area is going to be. However, that value can also be at a point where the draft is not maximum or the beam is not maximum. You have variations in shape that, particularly for hulls of this type, that a shape function that you're trying to use to describe kind of the central girth of the ship sometimes overly constrains what you actually want in terms of an outcome. So to keep hull geometry as simple as possible, I think it's important to have an objective in setting up the CAD geometry for optimization studies, that you look for a set of parameters or a parent shape that is really CAD friendly and morphing friendly, that you don't over constrain it, that you try to use the understanding of the physics of hydrodynamics to reflect some of those things that we know are going to have an influence: transom immersion, longitudinal center of buoyancy, the fineness of the nose, and not to overly constrain the hull, so that CAESES can do its job and really find those shapes in conjunction with a code like our analytical distributed volume method in NavCad to fit the shape of the immersed volume into an optimized setting.
Okay, thanks. I would just take one last. There's a few more questions coming in. Since we're already 10 minutes past the time, or a bit more than 10 minutes. There's one last question that I would like to answer, and then we will follow up on any questions that have remained open here. The question here from Philip is it necessary to specify a range for a constraint, such as a displacement, or can an equals constraint be used? For example, maintain a set target displacement or draft. It's not necessary to set a range. Sometimes there is a certain tolerance that is allowed for some of these values, and then it's let's say it gives you more flexibility if you can make use of that tolerance. So let's say if a little bit more or less displacement is not a problem, then why not giving that freedom so that you are able to have a wider design space that you can explore. But if you have a really tight constraint on a value like displacement, then of course there is also the possibility of keeping it exactly fixed. And we have also some special methods in CAESES where you can make sure that when you're doing changes to certain parts of the hull, that you do some, let's say, post-processing on the hull that readjusts the displacement to a fixed value, for example. So you can also define the constraint as fixed, but then as an equal constraint. But if you don't have anything that counteracts possible changes in displacement, then it will be very difficult during the optimization to keep it exactly fixed.
One quick comment on that. When we started this project, actually, we went at it with the idea of using an equivalency on a displacement to be fair to the original objectives of the design. But what we learned was that in the hunt for variations that hit the volume exactly, we were running many more iterations and variations than we needed to be. So the use of the Telfer coefficient, which normalizes resistance by vessel displacement, is a great way to improve the effectiveness of this kind of an analysis, because now you're looking at a normalized resistance. So in this particular case, our final hull was a few tons larger than our initial parent a displacement. And one way to resolve that is once the optimum shape is resolved, we can just use a geosim scaling to bring it down to the final displacement if we felt we needed to. Another example of over constraining something can sometimes make things work too hard.
Okay, thank you very much. At this point, I would like to conclude the webinar. As I said, we can be in touch about any questions that were left open here or that might come up after the webinar. Just one short request from my side. There is a short survey that will pop up when you will close the webinar. So of course, I'd appreciate your feedback there. Here I'm showing again our contact information. So we would be happy to hear from you and to start working with you and see how we can help you in your design tasks. And with that, I would like to say goodbye. And I hope to see you in another upcoming webinar or to hear from you. Bye-bye.